Welcome to Chapter 7. Today we start Laplace transforms. Laplace transforms are a great way to solve differential equations where the driving function is discontinuous. So far, all of the functions we've been dealing with when we solve differential equations have been continuous, but in real life, that's not really realistic. And so here are two examples, and don't worry, I'm not going to read through them all, but here are two examples where you might have a discontinuous driving function. One is a mixing example where the salt coming in is dictated by a valve, and that valve is either going to be on or off. And so the amount of salt entering or leaving the tank at time t is not going to be a continuous function. And you can read through that, but I came up with a differential equation here. And for circuits, using Kirchhoff's law, we have this differential equation for this RC circuit, but the electromotive force might be not continuous. So if it's a battery or if it's a switch, it's either going to be on or off. So in many electrical circuits, your driving function is not going to be continuous, and there's an example there. So this final picture on this page, you'll be able to go back in a few days and read this example, and it will make perfect sense. But for now, I'm just going to briefly go over it. And I'm using the mixing example as our example here. I've got the differential equation for the mixing problem up here, and we want to solve that. So we want to get x of t. That's our goal. So what we do is we send that equation through the Laplace machine. And when we send it through the Laplace machine, the little x's go to big X's. So you can see down here I have big X's, not little x's. And the variable t changes to s. So I have a new variable. So I send my differential equation through the Laplace machine. Then I have an equation with big X and s, and I solve it algebraically for big X. So I solve for big X. Big X of little s equals this, and then to transform the s's back to t's, I send it back through the Laplace machine in the other direction, so I go through the inverse Laplace machine, and I end up with the solution to my original differential equation. So this is going to require partial fractions, usually this step, so it's a little bit algebraically tricky, but nonetheless, we end up with this nice solution of our differential equation. And it's pretty easy to do. Once you know how to do these steps, very fast. Actually, on the last page of the notes, I solved this differential equation for you without using Laplace transforms, because it is possible doing it without Laplace transforms. So what we want to practice today is the definition of a Laplace transform. So how do you take the Laplace transform of a function? And then, so after we do the definition, just like derivatives have a definition, but then they have the shortcut rules. I'm going to show you the shortcut rules using the table. The Laplace transform table is somewhere in your notes. Here's a short version of it, but I think it's on the last page or the second to last page. This table, you're going to want to print out and keep it beside you when you do all your homework, because it's going to be like your Bible for this chapter. And I will give you that on tests. Don't worry. I don't expect you to memorize the Laplace transform table. Okay, so let's go to the definition of a Laplace transform. The Laplace transform of little f of t is the integral. So we take L of little f, and the notation is that's big F of s. Remember, the variable goes from t to s, and that's the integral from 0 to infinity of e to the negative st times f of t. And the domain of that function, big F of s, is the s's for which this improper integral converges. Yikes, I know, it sounds scary, but it's not, don't worry. All right, here's some notation. Every time you take L of a function, the little variable switches to a big variable. So the little f, we write big F. L of little f is big F, so shorthand would just be L of little f is big F, and it's understood that little f depends on t and big F depends on s. So here's another one. If you took L of little g, you'd get big G, And this is the one we'll use most often when we solve differential equations, because we're going to be solving a differential equation with like y prime or y double prime. And so we'll be taking L of little y, and that will be big Y. And again, t goes to s. So let's use the definition to find three Laplace transforms. These, the first two come from your table. If you look in your table, the first formula is little f of 1 is 1 over s. So that should be our answer. And let me show you how to read that table while we're here. Little f is on this side, big F is on this side. And so you could read this as the Laplace transform of 1 is 1 over s. So the Laplace transforms are in the second column, the functions are in the first column. Okay, so by the definition, and that's what a triangle over an equal sign means, it means by definition. By the definition, this is the integral from 0 to infinity of e to the negative st times 1. Now that's an improper integral. And in the past, I would have you rewrite that as the limit as k goes to infinity of the integral from 0 to k. And then we would find that integral and then finally take the limit. At this point in our mathematical careers, we're advanced enough so that we don't have to do that. We can keep writing infinity as our upper limit, and we just all understand that means the limit as k goes to infinity. We switch that infinity to a k and then push k out to infinity. So we're just going to leave infinity in our limits. So I integrated. Remember, the variable is t. So negative s is a constant. So the integral of e to the negative st is negative 1 over s e to the negative st. And I'm going to define that between, evaluate that between infinity and 0. And so that's going to give me negative 1 over s. And I'm going to pull that out. That's a constant. And then e to the negative s times infinity minus e to the 0, which is 1. Okay, e to the negative s times infinity. Now, as long as s is positive, this is going to go to 0 because e to, let's say like e to negative infinity is 0. So we want to keep s positive for this to converge, because if s is negative, then this would be e to the infinity, which is definitely not 0. That just blows up. So if s is positive, that's 0, and we get negative 1 over s, which is positive 1 over s. And we need s greater than 0. We're not going to really worry when we're actually solving differential equations with Laplace transforms. We're not going to worry about the restrictions on s. We're just going to assume that they're in the place that they need to be. But for now, I'm just going to write s greater than 0. Okay, next one, e to the 2t. So using our formula, the table says L of e to the at is 1 over s minus a. So in this case, a is 2. I should get 1 over s minus 2 when I use the definition. So let's see how that works. I took L of e to the 2t. That's the integral from 0 to infinity of e to the negative st times e to the 2t. In the next step, I combined the exponents. Okay, and now I'm going to integrate. My constant is 2 minus s. So I get 1 over 2 minus s e to the 2 minus s times t, and I'm going to evaluate between 0 and infinity. Okay, that's 1 over 2 minus s, and then I get e to the 2 minus s times infinity minus e to the 0, which is 1. Okay, I want that exponent of the exponential to be negative, so as long as s is bigger than 2, this is going to go to 0. It's going to be 0 if s is greater than 2. And so I'll get negative 1 times 1 over 2 minus s, which is positive 1 over s minus 2, which is what you would have gotten if you had used the table. All right, last one, you can't use the table on because there's no table entry for this function I have pictured here. So we have to use the definition. And so first thing I'm going to do is write down a formula for this function. F of t, it's going to be piecewise. All right, so it's a line going through the origin, slope 2, so that's 2t, and that's for t. I'm going to say, well, it doesn't matter whether you have less than or equal to or less than in any of your breaks, because the Laplace transform is defined as an integral, so it won't be affected by the value at a single point. So you can see here I left both of these dots hollow. So if I fill this dot in, then I'd say if t is between 0 and 1, and then the function is 0 once t is past 1. Okay, so if your function is piecewise and you want the Laplace transform of it, you're going to have to separate out your integrals. So I'm integrating, remember, we're going to integrate from 0 to infinity. So we're going to break that up into two separate integrals. We'll go from 0 to 1, that'll be one integral, and then we'll go from 1 to infinity, and that'll be the other integral. Now the nice thing about the second integral is it's from 1 to infinity e to the negative st times 0. The second integral drops out completely because the function's 0. So really we're just left with one integral going from 0 to 1 e to the negative st times 2t. So that's an integration by parts, which I did. You can read that. You might want to pause the video, read through my parts, read through my integration, and make sure you agree with what I got. Okay, so I'm down here now. I've evaluated my integral, and I'm going to evaluate this answer between 0 and 1. And so I'm going to get, now be careful here. The variable's t, not s. So you're plugging 1 and 0 in for t. So we're going to get negative 2 over s e to the negative s minus 2 over s squared e to the negative s minus, when we put in 0, we get 0 in the first part, and then minus e to the 0 is 1, so 2 over s squared. So putting it all together, I get positive 2 over s squared, and then I get minus 2 e to the negative s over s, and then minus 2 e to the negative s over s squared. And that's my answer. Now for your homework, you only have two problems where you have to use the Laplace transform definition to find the Laplace transform. And they're both piecewise defined functions. You'll have to do what I did in this last example. The trickier one is the second one, number 4 in your homework, I believe. And I did an example of that on the last page of the notes in case you're having trouble. You might have different numbers, but the integration is the same. Here's a solution to one of your homework problems right there. Okay, so now let's use the table. Okay, so this is the fun part. Laplace transform is linear. What does that mean? It means if you want the Laplace transform of the sum of two functions, like this example here, you can take the Laplace transform of each function and then add. Also, if you want the Laplace transform of a constant, like 2 times a function, pull the 2 out, find the Laplace transform of the function, and then multiply by 2. So we'll use those properties. For example, problem A here, you're going to do this step mentally. This is L of s sine 2t plus L of t squared. So you don't have to write that step down. If you just write your answer underneath this, I'm going to understand that you broke it up into two problems. The first one, you're going to use formulas. So if you go over here, I put a short version of your table over here so you can look at the formulas. This one looks like number 6 to me with b equal 2. And this one, you're going to use formula 2. Okay, so if we use formula 6 on this first part, we get 2, because that's my b, over s squared plus 4. And if we use formula 2 on this guy, 2 factorial is 2, and then s to the n plus 1. N is 2, so s cubed. That's fast. It's a lot faster than doing an integral. Okay, this next one, super easy. This is formula 3. Number 3, with a equal to negative 6. So 1 over s plus 6. All right. Next one is, this is my favorite formula, is number 5. And sometimes when you're starting out, this can be a little bit tricky. So it's helpful to write down what the parameters are. If you're using formula 5, n is 5, and a is the coefficient of t, which is negative 1. So we're going to want 5 factorial by formula 5 factorial over s minus a, was s plus 1, and then we add 1 to the exponent, and that's 6, and 5 factorial is 120, I believe. Okay, just a couple more. This next one, I'm going to use formula, let's see, 9, with a equal 4 and b equal 3. So this is going to be s minus 4 over s minus 4 quantity squared plus 9. Okay, next one, this is, I'm not going to write out L of 5 minus L of e to the 2t plus L of 6t squared. I'm just going to do the linearity part in my head. Now, L of 5, think of that, there's no formula for L of 5, but that's 5 times L of 1, right? Because 5 is 1 times 5. So there is a formula for L of 1, that's 1 over s multiplied by 5. So this first guy is going to give us 5 over s. The second guy, e to the 2t, so I'm going to want formula 3, 1 over s minus 2, and then plus for the next guy, for e, so L of 6t squared, pull the 6 out, L of t squared using formula 2 is 2 factorial, which is 2, so 2 over s cubed. So I have 2 over s cubed times 6 is 12 over s cubed. All right, and some of your problems, again, are going to ask you for the restrictions on t. If you have several pieces to your answer, you're going to use the most restrictive interval. So this first formula was for s bigger than 0. The second formula, if you look in your table, that was valid for s greater than 2. And the third one is s greater than 0. So for all of these to be valid, the most restrictive interval is s bigger than 2. So I'm going to use s greater than 2 so that that formula will be valid. Okay, just one more, and then I'm going to talk about what functions have Laplace transforms. And then at the very end, there's some practice for you to do, because the only way to learn how to use the table is to do it. So I've got some practice problems here with answers at the end, and they're not hard. They're just doing what I'm doing here. So this next one, I'm changing the verbiage a little bit. Find big F of s for little f equal this. Now that's just another way of saying, please find L of this function f of t. So it's another way of saying it. So I want L of, if I want L of this guy, there's no formula for that. First, I'm going to have to multiply it out using FOIL. Then I can use the table. So that's L of t squared, that's 2, plus 2t e to the t, plus e to the t times e to the t is e to the 2t. Okay, so now I can use formulas 2, formula 4 for the next piece with n equal 1 and a equal 1. And then the last piece is formula 3. All right, so L of t squared is 2 over s cubed. And now I want L of t e to the t, and I'm going to multiply my answer by 2. So L of t e to the t is 1 over s minus 1 quantity squared. So I'm going to get 2 over s minus 1 quantity squared. And then this last piece is 1 over s minus 2. I can do these pretty fast because I've been using the table for a while, but for you, it might take you a little bit longer at first till you get used to using the table. Okay, last topic. What functions have Laplace transforms? Well, most of them, but that's a little vague. Here are the restrictions. F has to be piecewise continuous and of exponential order. So what does that mean? First of all, piecewise continuous means you only have jump or removable discontinuities. You can't have asymptotes. This would be bad. No asymptotes. That's an essential discontinuity. So you need just nice breaks, okay? And then exponential order means the function doesn't grow faster. F does not grow faster than your typical exponential function that looks like a constant times e to the ct. So it doesn't grow too fast. Now, the reason for that requirement is, remember the definition of the Laplace transform. I go back here. It's the integral from 0 to infinity of e to the negative st times f. If f grows wicked fast, then this integral won't converge, right? So when you multiply by e to the negative st, you need to have a function that will converge on the integral from 0 to infinity. So you can't have a function that grows too fast. All of our functions will not grow too fast, don't worry. All right, so I just wanted to, just one more easy thing here before I let you loose. We're just going to graph this function and determine if it's piecewise continuous. So, and we'll determine it from the graph. So from 0 to 1, the function is 1, and it's an open dot at 0, straight line 1, fill in the 1. This is 1 here. Okay, then from 1 to 10, it looks like a parabola. And let's see, when t is actually 1, this would be 0. So I'm going to put a hollow dot there and then go up in sort of a parabolic arc. Here's 10. And this dot would be 10 comma 9 squared is 81. So that's what the function looks like on the interval from 0 to 10. Is it piecewise continuous? Yes. It's got a jump discontinuity right here. That's fine. No asymptotes. We're good to go. All right. So I'm going to let you loose. Next time we'll talk about using the inverse Laplace machine. So today we're practicing going in this direction. Then we want to learn how to go in this direction. Then we'll put it all together to make the big loop and solve differential equations.